Okay, so it looks like we're go. Thank you. Thank you, everybody, for being here today. Hope you're enjoying the conference as much as I am, and also thanks to NDC for having me today. So my name is Matteo. Today we're going to talk about code analysis, secure coding, and in particular, taint analysis. We're going to see how type systems and programming languages can be used to encode security properties and enforce them at compile time to make our code more secure by design. So I am a software engineer mainly. I've worked on many different applications in my career, from embedded applications to distributed ones. I'm mainly a Scala developer, so we'll see some Scala code today. Now I'm afraid to ask this. How many of you know Scala? Okay, 1, 2, 3. Okay, so we'll see some Scala code. We'll try not to get lost in type systems. I'll try to give you the general idea of what we want to do without, diving deep into types. What's important is that my academic path focused on type systems and on programming languages. So today I'm here to share with you the beauty and the power of type systems, showing how they can be used to encode and enforce security properties to have the compiler check for security violations, producing code that is secure by design and construction rather than by correction. And this is because data vulnerabilities are expensive. According to IBM's cost of a data breach report from this year, the average cost of a data breach was more than $4 million. Now, this includes different data breaches, small ones, big ones. It includes different types of costs. So it could be cost for looking for the vulnerability, for fixing the vulnerability, reputational damage, also cost for fees that you have to pay if you lose some data. But the point here is that data breaches are expensive. And they are expensive because the underlying data vulnerabilities are very difficult to find and to fix. Because our applications nowadays are so full of input. We are all about data. We fetch data from a huge variety of different sources. It could be users, could be your database, it could be your cloud provider, it could be LLMs nowadays. So you don't have the control anymore on the data you're entering in your application. And the worst thing is that depending on the technology and on the language you use, finding and fixing vulnerabilities might be even more difficult. So imagine if you are a C developer with a C-based application and you have a single input in your application. But then you have 10 different pointers reading the memory location where the input is stored, manipulating the input, reading it, writing it, and so on. So if you are to analyze all the possible data flows, you have to go through all the flows generated by 10 different pointers. And the number explodes if you increment the pointers or if you increment the inputs. So they are difficult to find. Also, nowadays, our applications are structured into components and into layers, and each different component has a very well-defined responsibility. So if you are developing, for example, a web-based application, you have maybe a controller reading the input from the request, coming from the user, and then you have a service layer somewhere deep in your application interacting with a DB. And these two components might be developed by different teams, different companies, if you employ contractors, and you might not know what happens between the controller layer and the service layer. There could be input validation, there could be input sanitization, there could be input manipulation of some kind. You don't know what happens. And so analyzing the data flows, even in simple applications, is very complex. Now, over the years, security researchers and practitioners have developed many different tools and analysis to track data flows. One of them is taint analysis. Now, I'm going to give you an extremely general and high-level definition of taint analysis, and that is on purpose. So taint analysis in this presentation is just a technique to track data flows of interest within your application to make sure that they are properly handled. Now, if you don't know what taint analysis is, and if you read this definition, you probably still don't know what taint analysis is. It conveys just too little information, But that, again, is on purpose, because we have so many different applications nowadays that it's difficult to determine, in many cases, what is a data flow of interest. And therefore, it is difficult to determine how to properly handle those data flows. I'm going to give you 2 examples. So the first one is information disclosure or data leaks. Now, in this case, what you have is you read the API key, for example, from a secure location. It could be your DB, it could be your cloud provider, your file system, and then you use this API key to build an API client. Now, this is a data flow already. We are reading something from an external source that we trust, and we're using it to build a client to a third-party service. Now, this might be not a data flow of interest, because we might trust the client, we might trust the service, we might not be interested in this print, for example, to analyze that data flow. So let's just not look at it for a moment, but then you have a very simple log message saying, hey, congratulations, you just created an API client with this API key. Now, this is a security violation, because even if your logs are not public, the people allowed to read your logs might be different than the people allowed to read your secrets. It could be other teams in your company, or it could be other companies as well. So you are disclosing information here. This is certainly a data flow of interest from a security standpoint. So how can we make sure that it is indeed properly handled? Well, we have different possibilities. One is to just forbid the data flow entirely. So you say, well, this is a vulnerability, please remove the log message, and that's it. Or you could mask the API key somehow, just printing a hash function, for example, of it, or printing just the first characters to make sure you're not disclosing the full secret. Okay, so you can see 3 lines of code. You have 2 data flows. One of them we are not interested in. The other has 2 possible ways to handle it. So it is complex to define how to treat these data flows. Now, the second example is the complete opposite. Here, you have an application that reads input from users. Now, imagine this is a file management application. So what you're trying to do is you read a file path from the user, and you delete the file pointed to by that file path. But now again, imagine you are developing a multi-user system application, and so a malicious user could enter a relative path pointing to the file of another user, or an absolute path pointing again to the file of another user. So what do you do here? You cannot just forbid the data flow, because this is a valid use case of your application. The application is supposed to delete the file. What you can do, though, is validate or sanitize this input to make sure it doesn't contain any relative path or absolute path pointing to other users' files. Now, as you can see, again, here we have a different data flow, a different way to handle it. So it's still, again, difficult to define properly what taint analysis is in generic applications. We can identify 3 main components, though. We have input sources that are where you fetch the input from. You have sinks, which is where you use those inputs. And then you have sanitizers or validators. And these components are responsible to enforce security properties on your inputs to make sure that they comply with, again, security properties and they're safe to use in your sinks. So in more general terms, taint analysis aims to track all the data flows from sources to sinks without proper sanitizers or validators in between. Okay? This is it. This is how it works generally. Now, if you are into security or code analysis, you will know that for everything, you have 2 possibilities. You either statically analyze your code, which means you run something on your code base and you don't run the code itself, or you use dynamic analysis, which means that you might not even have the code available. You just run some analysis on the running application. Again, with taint analysis, we have these 2 possibilities, And we'll see in a minute that we also have another possibility, which is more based on programming languages. Now, the main benefit of a static taint analysis is that it covers all your code base. You can run the analysis on the whole code base you have. It will look for vulnerable data flows. It will look for vulnerabilities, and it will report those vulnerabilities without running your code. However, depending on many factors, depending on your programming language, on the size of your code base, the analysis might take a long time to complete. There are some research results showing that static analysis can also take hours and be extremely resource intensive. The main problem, though, with static analysis in general, it is that it's undecidable. And this means you cannot rule out at the same time false positives and false negatives. Now, false positives here are data flows marked as vulnerable, which are not a vulnerability by themselves. Now, this requires programmers, developers, security experts to go into the code looking for the vulnerability, and this might be a lot of work, again, because the data flow might be complex. False negatives are worse, are data flows not marked as vulnerable, but that hide a security vulnerability. And what can happen is that your users find the vulnerability, and if they are malicious, they can exploit it without you knowing that what is going on in the application. So this is static analysis. And generally, what you do to mitigate the number of false positives or false negatives is you make assumptions on your code. And depending on the assumptions, again, the analysis might take even longer to complete if it's a very deep analysis. So generally speaking, what we do normally is we turn to dynamic analysis. In dynamic analysis, we might not even have the code because we can just analyze an application by observing its behavior while it's running. It could be in your testing environment, it could be on production, it could be on with real users, and dynamic analysis can flag vulnerabilities in real time. This is what happens. The problem is that in this case, for example, to look for vulnerabilities, we have to trigger specific data paths in your application. Now, depending on the input that you enter in your application, you might or might not explore all the data paths. So what you do generally is you combine dynamic analysis with fuzzing, for example. So you randomly generate inputs to explore, as much as possible of your application. But then again, the more inputs you generate, the more input you feed your application with, the longer it will take in general to analyze the application. So we'd like to look for a trade-off of these two different analyses, and the trade-off in some cases is language-based security. So with language-based security, the idea is that we don't need a third-party tool analyzing either our code or our application. What we do is we use the features of our programming languages to encode security properties and enforce them either at runtime, which is closer to dynamic analysis, or at compile time, which is closer to static analysis. We'll see in this presentation a form of language-based security closer to static analysis, because we'll try to use type systems to encode vulnerable data flows and have the compiler block the compilation whenever a vulnerable data flow is found in the code itself. In the end of the presentation, we'll see also some implementations of taint analysis in programming languages that are closer to dynamic analysis. So, the property that we'll try to enforce with our little framework is that if the code compiles, now we'll be using Scala, so it means that if the code is well typed, then we have no data flows using unsanitized values, so values we do not trust, in security-sensitive contexts. Now, this already identifies the data flows we are interested in. We are interested in those data flows flowing to things that could present security vulnerabilities. And it also depends, of course, on your application. How we make sure they are properly handled, we try to sanitize the values. So we try to forbid any flows without a proper sanitizer or validator, depending on the logic of your application. Now, we are software developers and engineers, so we like to start with some requirements. We'll model 3 main taint levels. We'll model tainted values. These are values fetched from external sources we might not trust. So we'll forbid tainted values in security-sensitive context. We'll have pure values. Pure values are inputs coming from sources we do trust. Could be UDB, for example. You could decide, well, I do trust my DB, and I do trust all the values that come from that source. And then we have sanitized values. Those are values you did not trust before, but then you run a validator or a sanitizer, and then you trust the input. Now, the difference between validator and sanitizer is that normally validation doesn't modify the input, and then sanitization does modify the input. But in general, you can talk of validation and sanitization. They're almost interchangeable terms. At least they are for this presentation. Now, we want to make sure that tainted values are safe to use only after being sanitized. And we also want to make sure that whenever we combine these labeled inputs, we preserve the taint level. So this means, for example, that if we combine 2 labeled values, one is tainted and one is pure, then the result will be tainted as well, because we cannot trust the result of a computation involving a value that we do not trust. Okay, so we'll see some Scala code now. Then we'll see a short demo with a web-based application that presents an HTML injection vulnerability. So we'll exploit the vulnerability first, and then we'll see how we can secure the data flow using the types that we'll see now. Now, the first thing we do is we model the taint levels. Now, taint levels, you can imagine them as labels that we attach somehow to our values. Now, in Scala, we model them with enums. These are more powerful than enums in other programming languages. You can imagine this as an interface taint level extended, implemented by 3 different classes. One is tainted, one is pure, and one is sanitized. So it's just a hierarchy of possible labels that we will, in the future, somehow attach to our inputs. Now, the second thing is taint propagation. Now, without looking at the type signatures here, imagine this is a type definition in Scala. Imagine it as a directive for the compiler. We are telling the compiler, whenever we use this type in the code, you have to go through these rules, matching 2 different taint levels. So, for example, if we use, again, tainted and pure together, the result will be tainted. Imagine it as a lookup table, where the compiler goes, whenever it has to type an expression, it goes in there. At compile time, P0 and P1 will be actual types, so the compiler knows the types it's working on. It goes through all the rules from top to bottom, and whenever a rule matches, for example, in the first case, the first rule match because tainted is the first type, it will return a type. So it's a lookup table the compiler reads at compile time to infer the type of an expression. Okay, this is helpful when we combine values because we want to propagate the type of the taint without having developers explicitly write the types, right? These are compile time directives to help developers write less code and avoid one of the common pitfalls with type systems, which is, being too much verbosity in the code, and so developers try to work around the type systems themselves. Another example is with pure and sanitized, and in this case, the compiler again goes through the first rule, doesn't match, the second, the third, they don't match, then it goes here, it looks for sanitized, and then it returns sanitized. Okay, so this is, again, the propagation. Now, this is just a way to model some labels. that we want to attach to our types. The way we do that, one way we can do that in Scala, is by creating, of course, a new class, a new type. Now, imagine taint tracked as a box. Okay, so you have your input, which has type A. You put the input into the box, and then you wrap the box with a wrapper, and that wrapper might be tainted, might be pure, or it might be sanitized. Okay, so the box that you have conveys two information about the value you have inside the box, that is your input, and about the wrapper that you have outside the box, that is your trust level, how much you trust the input that is inside of the box. Okay, so for the rest of the presentation, think of like these things in terms of boxes. You have values inside and wrappers around. The first function we're going to look at is a flat map function. This is how we combine values using boxes. So when you have a box and you want to run an operation on the value inside, one way you can do this is you unwrap the box, you take the value out, you run a function on the value, and the function returns a new box with a new wrapper. Okay, so this is how you chain normally operations in Scala on these types of definitions. And so this is what flat map does. It basically takes the value out of the box, it runs the function returns a new box, but that box might have a different wrapper around. So what you do, in general, is in the return type, we use the taint propagation. So this means, without the compiler, it doesn't matter what f the function returns, the type of the wrapper around the box will have to follow the rules that we specified before. This ensures that developers won't have to write much code, and that all the flow in your code will be safe, because it will follow the taint propagation rules that we defined before. And then we have a couple of constructors to build these boxes. We have the default constructor, which is apply, which is opinionated and returns a tainted box. So it's a value, it's a box where we don't trust the value. And then we have an unsafe constructor, and it returns a pure box. Now, you might say that this unsafe constructor is a way to work around the library and to bypass the security guarantees. And that is actually true, but looking for calls to unsafe is much simpler, much easier than looking for vulnerable data flows. It is something that you can spot during a code review. You can spot using a tool that reads your code. It is much easier than spotting a vulnerable data flow by itself. Okay, so we now have these boxes, values inside, and the wrapper tells us how much we trust the value inside of the box. Then we can sanitize the boxes. Now, what we do in Scala normally is we try to model errors as types. So the sanitization here introduces a new type, which is either, and you can imagine it as a fork. When you have an either in your code, from that moment on, you can have a left branch with an error. This is a type E. And you can have the right branch with a valid value. So what we're saying here, we're saying that whenever we try to sanitize a value, the sanitization function might return two alternatives. We either have an error in a sanitization, in which case we completely lose track of the tainted box. If there is an error during validation or sanitization, what we want to do is we want to drop the box entirely, because we cannot trust and we do not trust the value that's inside. Using it in your application would likely introduce a vulnerability. And the other possibility is, of course, we have a valid value, and the valid value will have now the sanitized wrapper around. So this is the meaning of the sanitized function here. We'll see an example afterwards. It simply basically unwraps the value, runs the validation function, and either returns an error or a new box. But the new box will have now a new wrapper around, telling us, OK, we can now trust the value that's inside of the box, because it complies with some security properties. Now, the last part of this library is probably the more complex, if you're not into Scala types, and is telling the compiler when it is safe to open boxes. Now, all of this will happen at compile time, so we need a way to tell the compiler, well, you can open these boxes only if they have a certain wrapper around. And this is what we do using this can-open interface, actually. We are just giving the compiler 2 empty instances of this can-open interface, saying, well, whenever you want to open a box, you can open it only if the wrapper is either pure or sanitized. Then we use it in our code, and this will make sure that anytime a developer calls the open function, the compiler will look for an instance of the can-open interface in its context. During compilation, it will find these instances only if the wrapper is sanitized or if the wrapper is pure. In those cases, the call to open will compile. If the wrapper is tainted, the call to open will not compile. So the compiler will stop a potentially dangerous data flow in the application, potentially spotting a vulnerability because sanitization is missing or because we did not trust the value in the first place. Now, after this long explanation of type systems, we can look at some code. Now, I took one of the examples of the Play framework. Play is similar to Spring in Java or to Symfony in PHP. It's just a way to define web-based applications. It will have a form asking the user to enter the name of a widget and its price. We'll see 2 versions of the application. One has an HTML injection, so we'll be able to inject some HTML code in the name of the widget. And then we'll try to secure the entire flow using the types that we just saw, so using these typed boxes to prevent the vulnerable data flow and to stop the compilation if we do not sanitize the input, making sure it does not contain any HTML code. So I will just show the vulnerable version before. So the UI is not great, but this is what the example gave us. So this is the name of the widget. We'll start first by entering a perfectly safe name, widget 4, and the price. So there is some validation being done on the inputs by the application itself. So for example, if I enter a negative price, then I will have, there you go, a validation error here saying that the price must be greater or equal to 0. So I can just enter a valid price, and it will create a widget and add it to the list. Simple enough. But what if I am a malicious user and I enter a widget name with some HTML code inside? So in this case, what we are trying to do is we are trying to color the number 4 using the color red. Okay, simple HTML code, but still code nonetheless. So I will just enter a valid price, and then if I click Create Widget, I manage to inject some HTML code into the DB. Actually, this is an in-memory DB, as you'll see, but again, there is no validation or sanitization stopping me from entering potentially dangerous HTML code inside. And this happens because in the code, is it readable? Can you read it? Okay. In the code, we have, this is our DB. Now, very simple, with some widgets are coded. And then we have our create widget function. This is taken as is from the example from the Play framework. And the vulnerability relies here. So here, we are just taking the widget out of the request. We are building a widget object, and we're adding it to our list without any validation. Now, how can we secure this code? Well, the first thing we can do is we can add some architecture and structure to the code. So we do add a widget repository. This is a common pattern in web-based applications. You still have your DB here, and notice that the type of the widgets is still the same. So we are not trying to add type overhead into your business model. We are just trying to add these additional types in the interactions that you have with your vulnerable services. Now you have this list widget method. It returns, again, it calls unsafe, and it returns a pure wrapper, because in this case we do trust our DB, so we are just returning a box with the widgets inside and with a pure wrapper around. So this is safe to open. But then we have the add widget method, and the add widget method operates on boxes containing widgets. Of course, widgets are our entities here. It operates on boxes with an arbitrary taint label. Okay, so they can have any wrappers around, but we add an additional constraint, and then we say it is safe to call add widget if and only if your compiler can open the box. And so again, we add this type constraint over here as a parameter of the function to tell the compiler when it is safe to invoke this function. And then as a matter of fact, we do invoke the open function here when we want to unwrap the value inside of the box and add it to our DB. Now, the controller gets now more complicated, so you still have, you still fetch the value from the request. This is where you create a widget. We can't just send this widget to the repository because it won't type check, because we have different types. So what we do is we create a tainted widget here. Now, of course, if we were to call unsafe here, then we would bypass all the security checks. But then again, this would be kind of easier to spot during a code review or using a simple linter or static analysis tool. Then we have this tainted widget. The type of the expression, I don't know if it's readable, is our box with a given taint level. So if we now try to add this widget as is without any validation, now you will see that the code will not compile. Because the compiler, now Scala type errors are a bit tricky to understand sometimes, but in this case, it tells us that there is no given instance of can open for our taint level tainted. So the compiler is telling us, well, you have this box, but this box is not safe to unwrap because you did not run any sanitization or validation on the input. So notice that, again, if we do call unsafe, then the code perfectly compiles because the compiler is happy because it has a tool to unwrap the pure box. So what we do is we run some sanitization to our value. In this case, it's more like validation. We are not modifying the input in any way. We are just saying, OK, well, look for any characters in the name of the widget that are not letters, digits, or blank spaces. So if the name contains any special characters, then return an error. This is this left here. Remember the branch. You're branching off, return an error, and completely stop what you're doing because it's not safe to work on the tainted value anymore. Whereas if you don't find any special characters in the name, then it's just fine to go on and have your widget as is. Notice that the type now is sanitized. Okay, and sanitized involves, if you remember, a sanitized wrapper around the box. Now, also notice that we are not specifying types anywhere here. Everything is inferred by the compiler without the need for developers to write explicit types. So the verbosity of the code is kind of reduced. It feels more natural to write the code like this without having the boxes all around the code base. And then, of course, you have to match on the sanitized widget. So if it's an error that you got, you will return an error to the user. And if it's if the value was safe, then you can just add it to your DB, and this call will now compile perfectly because the widget is now sanitized. So if we go back to our this is a different page with the same UI, if we now try to input again the code with the name with the HTML code inside, then we'll have, there we go, an error because the sanitization failed because our function recognized that the name contained potentially dangerous characters. Now, you can also adopt a different approach. You could modify the input in this case by escaping, for example, the HTML tags. This could be a possibility. You could just drop the special characters if you wanted. That depends on your requirements, ultimately what you want to do with your input when they don't comply with some security properties. And then again, if we now enter a perfectly valid name like this, you will have, there you go, the widget added to your DB. So this shows how this library can somehow help you write code that is safer and more secure. And it doesn't have to be employed everywhere in your application. Here we just try to create a more secure layer around the repository to protect the data flows going to a potentially dangerous sink, which is interacting with your DB. Now, the main problem in general with language-based security is that it strongly depends on your programming language. So different programming languages have different runtimes, different compilers, different type systems. So it's not possible to write a unique solution that works for every possible programming language. As a matter of fact, if you try to implement the same library in Java, then there is actually no way to tell the compiler fail if there is no, if it's not safe to open the box. Java's type system is not powerful enough to express these compile time constraints. So what we can do here, the only thing we can do is we can rely on runtime type identification. We can look if the taint level implements the can-open interface. Notice that here the taint level is, these are empty classes, and only pure and sanitized implement the can-open. But the only thing we can do is we can throw an exception at runtime to block the execution of the application. Here we could report a vulnerability, we could add logging, we could do stuff. But the point is, this is done at runtime, not at compile time. So depending on the language, you have different possibilities to enforce and encode your security properties. Now, this is not the only way to do that in Java. Actually, a couple of months ago, there was a paper published in the COOP conference, which is one of the largest Europe's conference on type systems and programming languages, doing taint analysis and taint inference using type systems in Java, using annotations. So also, the way you implement your language-based security checks depends on your languages and also depends on your expertise. Now, if you are in Java, annotations makes more sense than using boxes, type boxes, because Java developers are more used to annotations, right? Whereas if you are a Scala developer, some Scala developers don't really like annotations. We do like types more, so we try to add these type abstractions everywhere to encode properties on the code itself. So it depends on your expertise and on your team, and ultimately this is just, the only one important takeaway that you should have from this presentation is that security is a team effort. So whenever you have to pick a new tool, a new language, or a new analysis for your code base, remember that you have to work with people, developers, and that these teams, these developers, these colleagues have different expertise. They are familiar with different languages, with different tools. So you should try to pick tools or languages that everybody is familiar with. If you're trying to force developers to use a technique you're not familiar with, then you might find resistance. You might find people trying to work around your library. You might find people trying to bypass your security checks. Wherever, if you look for techniques that everybody agrees on, everybody's familiar with, then you probably have more people embracing your security checks and writing code that is more secure and safer by design and construction rather than by correction. So thank you very much. I think we do have some more time for questions. You will find the code of the short demo here, with also a link to the implementation, the full implementation of the box. And also find my email here if you want to email with some more questions after the conference. Thank you. Yes? Do we have a mic for the questions? We don't have a mic for the questions. OK. Yeah.
Very interesting. Obviously, that's very Scala specific. Two things. One is, how do you retrospectively add tainting to code?
Mm-hmm.
Secondly, what's the runtime cost of the additional checks? If you can't do it in compile time, what's the original runtime cost?
Well, I'll start from the second question. So the question was, what's the runtime cost for these checks if you cannot do them at compile time, and how you add these checks to existing legacy code? So the runtime cost depends on what you do. So if you just throw an exception that is almost negligible, it's just part of the workflow. If you start adding logging, reporting, that increases the cost. But that is also true for every instrumentation that you might do on your code. So this is why it's preferable to do that at compile time, right? Because it doesn't add any overhead well, it does add some overhead in opening these boxes, but most of that part can be optimized by the compiler, so it doesn't really, incur into performance degradation most of the times. As for how you do that on legacy code, that is indeed a problem. The good thing about these approaches is that you can add them in small portions of your applications. So you can start small by adding type systems, like more sophisticated types, in small portions of the application, the ones that you feel are more vulnerable, or the ones that you feel you want to focus on, and then you can expand from there to the rest of the application, of course. The good thing is that once you start to add types, you will have the compiler guiding you on what you need to change to have the code running again. Okay, so it is easier to, if you add a new type as a return type of a function, then the compiler will tell you that you have to change this, and that to have the call compile again. So you can be guided also by the compiler in your changes. Does that answer your question?
Yeah, I'm thinking about just basic, range checking of variables.
Yep.
Something you used to do.
Yep.
The challenge used to be, you can put that in. Debugging was expensive, so therefore you take it out once you validated the code was okay. So it's a bit of a, but having it in the code all the time, I think is the right way, because that gives you a little bit more control and a bit more secure, rather than just saying, okay, I do it for debugging, take it out, okay, well the hacker will then find the weakness.
Yeah, it's also for documenting the code, like the security checks that you have. Like if you use types, one of the other uses of types is documentation. So you have something in the code that tells everybody, yeah, I have to comply with these constraints for your code to run. Okay, so this is also a good thing.
Having strong typing.
Yeah.
Is really, some languages are really good and some languages are awful. And that's, Java are amazing by nature.
Yeah.
So it's a case of how you try and enforce things as part of the rules. So yeah, I was just thinking whether you could get AI to help.
Yeah, I actually did try to ask, so I also have another slide here. So I did try to ask Copilot to take the first vulnerable code, to take the box implementation, and I asked it to secure the code using that implementation. This is what I got. So I will take the pointer here. Notice that what Copilot did here, it created a new tainted widget using, without using the unsafe method. So it recognized that it was potentially unsafe to use. It added an example sanitization, and now in this case, it would replace the vulnerable characters, so it would just drop completely all the HTML tags. It would add some other validation in the price, and then basically it would do the same thing, opening the box, adding it to the DB almost automatically. It did not introduce the repository because it did not try to start with the code more. But in the end, it did a pretty good job, I think, in this case, because it was able to infer all the the constraints here, to infer a pretty good sanitization rules, and then in the end, it just used the right matches. So this it works very well. In general, you can be guided by AI as well to add your rules. Yes? Thank you.
In your example, after you sanitize your widget, you're matching on the left and right.
Yes.
Will Scala enforce checking for errors before at compile time, or will it allow you to progress, assuming the result is successful?
Yes. So yes, when you match, I can go back to the code. When you match to left and right here, first, Scala will tell you if the match is not exhaustive. So in this case, it recognized that either can only be either left or right. So if you just have right, it will give you a compile time warning. Compile time warnings can be turned into compile time errors with a flag. So that is something you can do. And here, when you match for left, for example, error is just a string. It is not the box anymore. So in this case, you completely lose the tainted widget. Of course, you still have this variable. You can use it anywhere in your code. Again, but its type doesn't change. Its type is still tainted. So even if you can use it, you still have to sanitize it again, possibly with different rules, right? It doesn't have to be always the same rules. But in this case, with this sanitization, in this branch, you will completely lose track of your tainted value. Does that answer your question? Yeah. Okay, good.
And the second one is, you've done the same exercise with Java.
Mm-hmm.
Have you had a chance to look at other programming languages to see which ones you'll be able to implement?
No, actually, no. I looked if there were something for C# similar using types. Didn't find anything. I just found some static taint analysis tools similar with C++. So no, I didn't look into other programming languages specifically. I know this is possible with Haskell, not surprisingly. So actually, this work was based on a previous work I did with Haskell back at university. As I was saying, it was a bit less sophisticated, but still the type system that Haskell has is even more powerful for some things than Scala's. So not surprisingly, you can do that on Haskell as well. As for other languages, no, I wouldn't know.
TypeScript is like usually more flexible than C# and Java. I wonder if that would be one of the languages with something that has to be implemented.
Come again? What did you see?
TypeScript is usually more flexible
Oh yeah,
with types. I wonder if this also might be.
it could be possible. I will look into that. That's a good suggestion. Yes. Also because Scala these days is used in many contexts, but it's not as nearly as popular as, for example, TypeScript, right? So it would be good to see if that can be implemented also in other more dynamic languages, like if you pass the term. Thank you.
I think Matteo tried to do something for Python.
No.
I've not tried it, but I think they've tried to do taint analysis on Python with
Okay.
ISA or Python or something, because they've got massive Python code base and PyTorch and stuff like that. So that's probably why they've tried to do it.
That makes sense. So in general, you have different tools for any language has its tool for static taint analysis or dynamic taint analysis. There are, for C++ and Qt, there is also a dedicated tool. What they do is usually they look to the code and try to see if there is some data flow that is not sanitized. They also try to see if there is a function that can look like sanitization. There are some heuristics to say, well, this looks like sanitization, this doesn't look like sanitization. But then again, those are big tools. And when you start using static analysis, you have to do it on the whole code base. There are some research work showing that incremental static analysis doesn't really work very well. There's a lot of false negatives sometimes. So what you try to do usually is you have to apply it to the whole code base, which, again, we go back to the first problem where static analysis can take hours to complete, right? So if you do that on a massive code base, it could take hours. It's not something that you can do, for example, a part of a deploy pipeline as you go, because if it takes hours, you have to wait hours for the analysis to complete. So the good thing about using types is that everything is offline. When you run the analysis, you are still writing the code during your development cycle. So that is also a nice thing. You're not slowed down any more than you're normally slowed down when you have to type stuff and they don't type. Any more questions? Yeah? It could be just two states, safe and unsafe. Actually, the annotation example that I showed from the paper, they use just two states, tainted and untainted. I just wanted to model the fact that some values could be trusted by default without any sanitization. Ultimately, it could be dropped. It's something like null in Java. It didn't hurt to have it, like now. But then in retrospective, maybe it's not. It's surely not necessary. It just adds more, flexibility to the whole thing. Also, if you dropped pure, you wouldn't need the unsafe constructor anymore. So that is also a good point against having pure in the implementation. Any more questions? Okay, so I think we can all go to lunch, and I'll be around for the rest of the day. So if you have any more questions or thoughts, please do come to talk to me. Thank you.